Welcome dear students. In this topic we are going to deal about data warehouse architecture and the multidimensional data and the model data warehouse architecture. First let us see what is multidimensional data. The multidimensional database is a type of database which is optimized for the data warehouse and online analytical processing tool. To be more clear, a multidimensional database uses the idea of data cube to represent the dimensions of data which is available to the user. It consists of the following topics. Let me explain you the topics. The first one is the logical multidimensional data model. The second one is the relational implementation of the model. And the last one is the analytical workspace implementation of the model. First let us go through what is the logical multidimensional data model. A multidimensional data model is the most important part of online analytical processing tool. OLAP is an online processing tool that provides instant answers for the users. The analyst posts repeated queries during interactive sessions. OLAP is analytical and the queries are more complex, and so the multidimensional data model is designed to solve the complex queries in real time. A multidimensional data model is important because it provides simplicity. The central attraction of the multidimensional model of a business is its simplicity. That simplicity is the fundamental key that allows the users to understand databases and allows the software to navigate the databases very efficiently. A multidimensional data model is composed of logical cubes, measures, dimensions, hierarchies, levels and attributes. The simplicity of the model is inherent because it defines objects that represent in real world business entities. The analysts know which business measures they are interested in examining, which dimensions and attributes make the data meaningful, and how the different dimensions of their business are organized into levels and hierarchies. Here we can see the logical multidimensional data model diagram. The cube is divided into two types where it has two attributes. One is measures and the other is dimensions, where the dimensions has three different attributes such as dimension attributes, levels and hierarchies. First let us see what is logical cubes. The logical cubes provide a meaning of organizing measures that have the same shape, which means they have the exact same dimensions. Measurement is the same cube, have the same relationship to other logical objects, and they can be easily analyzed and displayed together. Then let us see what is logical measures. A measurement populates the cell of a logical cube which the facts of collected about business organizations. Measures are organized by dimensions which typically include a time dimension. An analytical database contains historical data, usually derived from a data in a legacy, transactional database, syndicated sources and other data sources. In the measures of static and consistent, while analysts are using them to inform their decisions. They are updated in a batch with the regular intervals, either weekly, daily or periodically throughout the day. Many of the applications refresh their data by adding periods to the dimension to the measure and may also roll off an equal number of the oldest time periods. Each updates will provide a fixed historical record of a particular business activity for that interval. Other applications do a full rebuild of their data rather than performing incremental updates. The base level of that determines whether an analyst can get an answer to the question. For this particular question, time could be rolled up into months and customer could be rolled up into regions and products. The products could be rolled up into items with an attribute of color. However, this level of aggregate data could not answer this question. At what time of a day are women most likely to place an order? An important decision is an extent to which the data has been pre-aggregated before being loaded into a data warehouse. Now let us see what is a logical dimension. A dimension contains a set of unique values that to identify and categorize the data. They form the edges of a logical cube and they measure within the cubes, because measures are typically multidimensional and a single values in a measurement must be qualified by a member of each dimension to be meaningful one. For example, the sales measure has 4 dimensions: time, customer, product and a channel. A particular sales value only has a meaning when it is qualified by a specific time period, a customer, a product and a channel. Now let us see what is logical hierarchies and levels. A hierarchy is a way to organize the data in different levels of aggregation. In the viewing data, analysts use the dimension hierarchies to recognize trends at one level, drill down to lower levels to identify the reasons for these trends, and roll up to the higher levels to see what effect these trends have on a larger sector of the business. Each level head represents a position in the hierarchy. Each level above the base or most detailed in level contains aggregate values for the level below it. The members at different levels have a one-to-many parent-child relation. For instance, Q1 and Q2 are the children of 2002, thus 2002 is the parent of Q1 and Q2. Suppose a data warehouse contains a snapshot of data which is taken 3 times a day, that is every 8 hours. The analyst might have been normally preferred to view the data that has been aggregated into days, weeks, quarters or years. Thus, the time dimension needs a hierarchy with at least 5 levels every time. Similarly, a sales manager with a particular target for the upcoming year might have been allocated that the target amount among the sales representative in his territory. The allocation requires a dimension hierarchy in which individual sales representatives are the child values of a particular territory. Hierarchies and levels have a many-to-many relationship. The hierarchy typically contains several levels and a single level can be included in more than one hierarchy. Now let us see what is a logical attribute. An attribute provides a piece of additional information about the data. Some of the attributes were used for display. For example, let us see, you might have a product dimension that uses stock keeping units, which is abbreviated as SKU for dimension members. The store keeping units are an excellent way of uniquely identifying thousands of products, but they are meaningless to the most of the people if they are used to the label data in a report or a graph. We would define attributes for the descriptive labels. Now, we might also have attributes like colors, flavors or sizes. This type of attribute can be used for data selection and answering the questions such as, let us consider a question now, which color were most popular in women's dresses during the year of summer 2005? How does this compare with the previous year's summer? So this is the question. Time attributes can provide more information about the time dimension that may be useful in some type of analysis, such as identifying the last day or the number of days in each of the time periods. Now let us see the relational implementation of the model, how it is implemented. The relational implementation of the multidimensional data model is typically a star schema. A star schema is a convention for organizing the data into dimension tables, in fact tables, and materialized views. Ultimately, all of the data is stored in columns and metadata is required to identify the columns and that function as multidimensional objects. In Oracle database, we can define a logical multidimensional model for the relational tables. We are using the OLAP catalog. The metadata distinguishes level columns from attribute columns in the dimension tables and it specifies the hierarchical relationships among the levels. It identifies the various measures that are stored in columns of the fact tables and aggregation methods for the measures, and it provides display names for all the logical objects. The next topic is dimension tables. A star schema stores all of the information about a dimension in a single table. Each level of a hierarchy is represented by a column or a column set in the dimension table. A dimension object can be used to define the hierarchical relationship between two columns that will be represented in two levels of hierarchy without a dimension object. The hierarchical relationships are defined only in a metadata. Attributes are stored in columns of the dimension tables. A snowflake schema normalizes the dimension members by storing each level in a separate table. The next topic is fact tables. Measures are stored in a fact tables. Fact tables contain a composite of primary key which is composed of several foreign keys and a column for each measure that uses these dimensions. Next we are going to see about materialized views. The aggregate data is calculated on the basis of the hierarchical relationships defined in the dimension tables. These aggregates are stored in separate tables which is called as summary tables or materialized views. Queries can be written either against a fact table or against a materialized view. If a query is written against in a fact table, that requires aggregate data for its result set, the query is either redirected by query rewrite to an existing materialized view, or the data is aggregated on the fly. Next, the analytic workspace implementation of the model. The analytical workspaces have several different types of data containers such as dimensions, variables and relations. Each type of the container can be used in a variety of ways to store different types of information. For instance, a dimension can be defined an edge of a measure or store the names of all the languages supported by the analytical workspace or all of the acceptable values of a relation. The dimension objects are themselves as one dimensional list of values, while variables and relations are designed specifically to support the efficient storage, retrieval and manipulation of the multidimensional data. Like relational tables, analytical workspaces have no specific content requirements. You can create an empty analytical workspace, populate it only with OLAP DML programs, or define a single dimension to hold a list of values. It describes analytical workspaces that comply with database standard form. Next we are going to see about a multidimensional data storage in analytical workspaces. In the logical multidimensional model, a cube will represent all measures with the same shape, that is the exact same dimensions. In a cube shape, each edge represents as dimension. The dimension members are aligned on the edges and divide the cube into cells in which the data values are stored. In analytical workspace, the cube shape also represents the physical storage of multidimensional measures in contrast with two-dimensional relational tables. An advantage of the cube shape is that it can be rotated. There is no one right way to manipulate or view the data. This is an important part of multidimensional data storage, calculation and display because different analysts need to view the data in different ways. For instance, if you are the sales manager for the Pacific Rim, then you need to look at the data differently from a product manager or a financial analyst. Now you can assume that a company collects the data on sales. The company maintains records that quantify how many of each product was sold in a particular sales region during a specific time period. Here is a picture that shows the comparison of product sales by city. The comparisons of the sales of various products in different cities for the year January 2001 and February 2001 can be seen here clearly. This view of data might be used to identify products that are performing very poorly in certain markets. Here is a next diagram that shows the comparison of product sales by month, which can be used to identify the products that are performing poorly in certain markets. A cube shape is three-dimensional. Of course, measures can have more than 3 dimensions, but 3 dimensions are the maximum number that can be represented pictorially. Additional dimensions are pictured with additional cube shapes. The next topic is database standard form analytical workspaces. Here is a diagram that shows how dimension, variable, formula and relation objects in a standard form of analytical workspace are used to implement the multidimensional model. Measures with identical dimensions compose a logical cube. All dimensions have an attributes and all hierarchical dimensions have a level of relations and self-relations. For clarity, these objects are shown only once in the diagram, where variables and formulas can have any number of dimensions. 3 are shown in this diagram. Now let us see what are the different dimensions of analytical workspace. Before that, let me tell you what is a dimension. A dimension in an analytical workspace is a highly optimized one-dimensional index of values that serves as a key table. Variables, relations, formulas which are stored the equations are among the objects that can have dimensions. Dimensions have several intrinsic characteristics that are important for the data analysis. Those characteristics are referential integrity, consistency, preserved order of members, and the last one is highly denormalized. Use of dimensions in standard form analytical workspaces. In an analytical workspace, a data dimensions are structured hierarchically so that data at different levels can be manipulated for aggregation, allocation and navigation. All dimension members at all levels for all hierarchies are stored in a single data dimension container. For example, month, quarters and years are all stored in a single dimension for time. The hierarchical relationships among dimension members are defined by a parent relation described in analytical workspace relations. As a one-dimensional index, a dimension container has many users in an analytical workspace in addition to dimensioning measures. A standard form analytical workspace uses dimension to store various types of metadata such as lists of hierarchies, levels and the dimensions composing a logical cube. To conclude, the major dimensions are the logical multidimensional data model, the relational implementation of the model and the analytical workspace implementation of the model. Multidimensional data mining, also called exploratory multidimensional data mining, integrates core data mining techniques with overlap based multidimensional analysis. It searches for interesting patterns among multiple combinations of dimensions attributes at varying levels of abstractions, thereby exploring multidimensional data space.